thick. We make them, when they cast the concrete, they use, at least in the US, they use something called a screed pole.
Wow.
So that it's a equivalent, constant thickness. So that the slab is, say, 225 thick the whole way. It doesn't.
So they don't cast it flat.
No.
Okay.
No. Yeah, so they have to set target heights so that the top of the slab is following, so equal thickness, 25 mm kind of hump. There was a question in the back.
One last.
Oh, sorry. Sorry. We'll come to you next.
What's the effect of depression on your pre-stressing?
Yeah, I mean the analysis would tell you that there isn't a big effect in the performance. It's more of about coordination issue. Trying to keep them away from columns, trying to keep them away from high points in your post-tensioning system. If you have a slab depression in mid-bay, let's say, not so much of an effect. I mean, it's less weight, right? Because we've taken some of the thickness out. Because we do everything we possibly can to keep the soffit flat. And for doing that, we also limit the amount of that depression, what it can be. Typically, we try to push the architect to only 25. Sometimes they ask for a little more, depending on the system, maybe we go a little bit more. But what we want to very much avoid is then lowering the soffit. If they came in and said, hey, we need 150 mm depression, which happens sometimes for certain things like trench drains or other unique conditions, there we may have to adjust the actual bottom. But we try as much as we can to just keep the bottom flat to simplify the formwork.
So you don't take them into analysis.
We do. We do. Yeah. So
local moments.
We include the reduced thickness in the analysis as well.
We, at least at an initial conceptual level, if you can conceptualize the slab and say the tendon layout, assuming that those depressed areas are openings, a hole, and get the system to work as if it were just an opening in the slab, and then put mild steel reinforcing steel to fill the opening. At least conceptually, if you can convince yourself that that works, you're good. Now, in the end of the day, when you do the final design of the post-tensioning, maybe that's not exactly how the tendons are laid out, but that's a really good test to see if, am I doing something that, yeah, this is going to easily work, or am I way out of bounds? Because if I can't imagine ever putting a hole in this location, I should probably not put a depression in this location. Anyway, that's the way we commonly think about it. Last thing I'll say on this subject is that when we put post-tensioning in a slab, one of our design philosophies is to have the post-tensioning kind of respond to the global performance, but not try and manage every little kind of localized nuance of an opening or a cantilever or a re-entrant corner. Do all the localized nuances of the design with rebar, and let the PT respond to the kind of overall performance. Because we find if you start trying to solve all the local problems with the PT, you end up inadvertently causing other problems. So don't try and get too much finesse with the PT. It's just keep it simple, and then do all the rest with the mild steel. Sort of in the back.
Yes. I think in your design of the building in Philippines, I guess the width of the steel wall might be around 6 to 8 feet or something. Actually, different. And the problem is, in my opinion, do you consider, because of if the shear wall is deflected, so there is a two different level. Do you consider it in this calculation, and how to overcome with the possession?
Sorry, when you say two different levels, could you elaborate what you mean?
Yes, because you see, because of the deflection, right? And this is long, right? So there is a difference deflection between it and this one.
So you're saying in an earthquake, in a seismic event,
yeah,
when you have the drift. Yeah.
Because it's rigid, right?
Right. Yeah. I mean this.
So deformed body.
Right. So this goes to a lot of the discussion about the research that's done on this drift ratio
Yes.
And limiting that drift ratio to the prescribed criteria that we have, you know, it's 2% depending on what we're looking at. And if we limit the drift ratio of the building to that, that's kind of what all of the testing and such is based upon. The testing of the column to slab connection, the testing of the shear wall to slab connection was done with that in mind, with whether it's 2.5% or however much, that the testing, the research reflects that amount of drift. So even though the other side of the building is up and this side is down, it's similar in the drift ratio perspective.
The second question. In the SCE, right, there is a law for maximum base shear is by amplification by omega 0. Right? Omega 0 is between 3 something. Based on your several examples in your design, based on performance-based design, what is the maximum base shear in comparison to the omega 0? I think it's better. The best one is similar, right?
Yeah, so
From the experience.
yeah, I'll take that. It varies by building and by site. And I'd say on the low side, the amplification is around 2. On the high side, it might be as much as 5.
Why?
This is the reason, one of the reasons why performance-based design is really good and important, is because the code omega 0 is a one-size-fits-all. And it doesn't recognize the specifics of your building. And in some buildings, the code may not be safe. In other buildings, it's too conservative. But performance-based design allows you to unlock that and actually make what's appropriate for your building. And it may be more, maybe less. But at least it's more thoughtful. And so one thing I'll point out to you, this is a little bit of a tangent, but just kind of signs of things to come. It's been known for many, many years that the predicted shear demand on shear walls is grossly underpredicted by a factor of some amount. Anyway, in the ACI 318.19, the new code, there's now a provision, there's a shear amplification provision to try and address that subject. Again, this is a committee number, so it's a negotiation. It's not science. It's like going to the, UN and negotiating a peace treaty. So the number is 2.5. What's printed in the code is 2.5. And once again, if you go to prescriptive design in the future, it will require that you multiply by 2.5 for the wall shear demand. If you go to performance-based design, then of course that's off the table and you explicitly evaluate that. Anyway, that's a very kind of tangential comment, I suppose. But I know you all are guided by the similar codes that we're guided by. So I wanted you to just be aware this is coming.
Okay, sorry, just to, as an additional question for what he asked, is there any minimum base year for the performance-based design? Because we are struggling with minimum base year. Yes, minimum.
This is outside the scope of this meeting.
Yeah,
today.
sorry, yeah. Well, yeah.
We know this is a very hotly debated topic.
Yeah.
And we could have a whole seminar on just that topic. I kind of maybe leave it at this, and then maybe we'll come back another day, and then maybe hockey will sponsor
Sure, why not?
Minimum base year. So, the numbers in the code, right? It's all made up. And it's all made up by committees. They all mean well. I sit on these committees. We all mean well. But they're gross simplifications of a very complicated problem. And so applying minimums and even maximums, these limits, are very artificial. And so this is, again, the power of performance-based design, where you take your geometry in your building and then you explicitly evaluate the hazards at your site, whether it's seismic or wind or what have you, and then put the demand and the capacity together explicitly and interrogate the design. And in that case, these minimums and maximums have no bearing, because I'm using science and physics and reliability to really do proper engineering. So CS minimum, throw it away. All right, so that all said, there is a rationale for from a stability point of view, a lower bound, a number which you should not go below. And we see these, for example, in codes that don't even talk about seismic engineering. The British code for decades has had something called a notional load. The American code has something similar as well. And in the American code, it's 1% of the building weight. In the British code, it's 2% of the building weight. Okay, those are rational numbers as a lower bound, that in no case whatsoever should the base shear drop below, say, 2% of the building weight. Okay, I accept it. Because in reality, in a seismic zone, you'll never be below 2%. It will always be 3, 4, 5%. But if somebody wants to hang their hat on a CS minimum hook, talk about that kind of stability threshold. Okay, we have another session on R factors and CSBS minimum and these sorts of things.
Thank you.
I asked Sir David to sponsor the hockey
Sure.
seminar.
Is
Sorry.
it-
Yes.
I would like to know what kind of analysis you use when you performing PBD. Is it a pushover analysis or non-linear time history analysis? This is the first question. The second question is what is the difference when you model unbounded pre-stress or bounded pre-stress in terms of non-linear characteristic as well as acceptance criteria you use?
Yeah, so in the performance-based design, we don't use pushover analysis. We don't think it's appropriate for high-rise building, just because of the higher mode effects. It's very difficult to capture that properly in a pushover. So we use nonlinear time history analysis when we do the performance-based design evaluation. And in that, there's not necessarily a lot of differentiation we put on bonded versus unbonded related to the acceptance criteria for performance-based design aspects. There are certainly gravity design related differences in the systems. Effective stresses, different friction losses, there's different things involved that are different in those systems. But when it comes to the performance-based evaluation, the drift limits, we don't have a differentiation between the two systems.
Yeah, and then kind of further on that, there's 2 or 3 or 4 software packages out there in the world that will facilitate these nonlinear response history analyses. The one that we've been using for the last 20 years or so has been Perform, which is a CSI product. So the people that write ETAPs sell that product. These days we're looking at a few other packages that we may change to in the future. LS Dyna is the name of one of the programs, and the other one's called Abacus. And they're very, very powerful nonlinear finite element programs. Anyway, to date, at this moment, as we sit here, we still use Perform. But we're probably going to move away from it in the next year.
Next.
Before you do performance-based evaluation, you have to have some sort of a preliminary design before you start running the analysis, right? So in US practice, what would be the criteria to perform this preliminary design?
So in our view, the right answer is that our preliminary design, or you might say lower bound, is based upon the greater of either the service level earthquake, so the 1 in 50 year earthquake, and the wind load. So those two lateral loads are what we typically would like to base the preliminary design on. And this is widely accepted in Los Angeles and a few other areas, but there are other certain jurisdictions that feel that that's too low for their lower bound, and they do require some of the preliminary design to be done using the design base earthquake, so the 500-year-ish preliminary design.
We, as you know, the Los Angeles Tall Buildings document, the guidelines, and the latest version of TBI say that it's not necessary to use the code DBE analysis, if you will. And that's a recognition of what I mentioned earlier, that the R factors are committee negotiation. They're fictitious numbers of convenience to facilitate elastic analysis. It has no really bearing on reality. The trick and the part to be very cautious of is that depending on the site, the difference between the service level earthquake demands and MCE demands can be substantial. And you can get surprised where a design you think is well proportioned and meets the service level earthquake objectives, when you interrogate it at MCE, it fails. In the US, a location where that gap between the frequent earthquake and the big earthquake is very large is in Salt Lake City. It's huge. And so if you were to proportion a building for service level earthquakes in Salt Lake City without a very keen appreciation of what's to come, you're going to be surprised. It's not as big a gap, say, in Los Angeles or in Manila. Anyway, it's something to be very cautious with. If you eliminate that kind of DBE check, which we totally support, that's the part that you need to be really careful and thoughtful about. Sean has a couple of techniques that you use, the one that you use. Why don't you describe it?
Yeah, I mean, in the end of the day, we do the performance-based design evaluation using the MCER criteria, level of earthquake, right? And really what we're trying to determine is how much energy dissipation, how much inelastic behavior happens in the building, dissipates off of that MCER behavior and dissipates energy, so lowers the base shears, basically, right? So we've been tracking in our designs, after we complete the performance-based design evaluation, we look at the base shear of the building and compare it to the elastic MCE analysis and calculate what we call effective R. Effectively, that's what the R factor is, right? Is I'm taking this and I'm lowering it. We're saying, well, what do we get when we take the MCE and we lower it to what the actual behavior is when we consider all the energy dissipation? So we calculate that explicitly at the end, just to inform our designs in the future. So we've been doing this for a while, and we find numbers that there's a difference, right? Every building is going to behave differently. But so, for example, in Manila, that number of elastic base shear compared to the nonlinear base shear is somewhere about 1.5. Sometimes it's less, sometimes it's more, but that helps us when we proportion initially to make sure our walls are thick enough, because we know that's going to be where we get to in the end. So we're starting to do this more frequently because it just helps us proportion better in the beginning, so we don't get surprised at the end of the performance-based design and have to go change walls.
Another technique that we've used, just again to inform thinking, is to take an elastic model and run MCE on an elastic model. And look at what the DCRs are, what are the demand levels with MCE and an elastic model. And it just gives you some appreciation for how hard am I going to maybe push this building later. Of course, that's fictitious again, right? It's not real, but it's almost an upper bound analysis, because as energy is dissipated, some of the air comes out of the balloon and you don't push elements that hard. But it at least gives you a feel. And it's a very quick and dirty way to go about it, right? So you're not running long time history analysis, you just run MCE spectra at an elastic model. Maybe behind you.
With me?
Yes, you. You.
Thank you.
You.
My question is about if you try to use, let's say, a seismic building device seismic building device in combining with this flat slab design, especially let's say in Manila, which is the seismic maybe almost same like Indonesia. Have you any experience, and have you compared it and make a comparison between without seismic building device like such a damper, yeah, or with the seismic design?
Yeah, there's a number of buildings, in particular, I guess Manila has quite a few now that have these damping devices being implemented. And yeah, it's very critical to compare the behavior with and without, so you understand, does it make sense on this project to do? Because it doesn't make sense for every project. And I guess what we found is that most projects, it doesn't make sense. It's only unique projects, maybe very slender, have a very big slenderness ratio, or other kind of unique aspects that kind of lead you to deciding that it's the right answer. And the performance is a good question in that, is how is one going to perform better than the other? Even though they both meet the objectives of the code, you might find that the one that has a damping system might perform even better than the code, which some building owners might want, even though there's typically a higher upfront cost when you put a system like that in. But I guess our job as engineers is to probably educate our clients as to, yes, you can spend a bunch of money and improve your building behavior, but you still meet code even if you don't put that in. So, does that help answer your question?
No, but sometimes using this seismic building device could also save the cost of the upper structure itself. That is why I asked if you have experience in comparing these two kind of system, the conventional system using shear walls and combining with the seismic building device.
Right, we've looked at probably every system that's out there. So Taylor devices and the hydraulic dampers, Taylor devices with a lockup system, the Kinetica system, which is the viscous coupling devices. We commonly use often buckling restraint braces as an energy dissipation mechanism, because they're fairly comparatively less expensive but very predictable performance.
Yeah.
And as Sean pointed out, for each building, the best design that achieves the owner's objectives changes from building to building. It's not like, oh, we'll put VCDs in every building now. Well, Connecticut would love us, but it's not the right answer necessarily, right? So for us, at least, on each building, we study different systems and try and figure out what's the most effective one for this particular building, given this particular site and shape and geometry. But they can be very effective, right? It's more a matter of kind of a cost benefit.
Thank you.
Yes.
My question is it is limited in the stressing stress in the flat slab. The second question is you mentioned about the flat slab system is economical, but in the design to achieve the drift and everything, if you use a flat slab, it means you make it bigger in the wall. And also in some cases, the flat slab is not reduce the weight, because the thickness of the slab comparing to the conventional beam slab is more thick. That is why it's more weight, and otherwise it's also maybe it's for the lateral resistance unit bigger compared to the conventional.
Sir, can you go over that first question again? You said the stress?
Limited of the
I think the stressing force.
stressing force.
They require
The pre-stress density in
It is also in the
Effect
column
of stress.
in the column strip. It is
Right.
maybe limited or not?
Yeah, so, I'm gonna struggle to do the metric conversions. I mean, the code says that there is a minimum amount of pre-stressing force. The ACI code says there's a minimum amount of pre-stressing force that you should apply to even be considered a post-tension slab, and that's 125 PSI, is the minimum amount of post-tensioning. And the code doesn't actually have a maximum amount of post-tensioning, but there's a recommended maximum of 300, is usually what our target is. Sometimes it goes a little bit more, depending on the needs. When you go much more than that, you start to run into lots of other things that you need to be more concerned about, anchorage issues or over stressing. That's one of the things we didn't really talk about here, but the overbalance. And the idea behind the balancing is you balance out the self-weight of the structure, right?
Mhm.
But when the self-weight, particular buildings here, a lot of the self-weight component, the dead load component is the screed slab and the block wall partitions. And those tend to not come in until after the stressing operation is done. So you have to be very careful that you don't overstress the slab and then create problems on the underside because you've overstressed. So anyway, that's the range that we usually operate in, is the 125 to 300 PSI stress range.
Sorry, Chair, but how about for individual strength? Do you have any maximum figure that?
Yeah, so typically at the anchorage, the time of anchorage, the stress that we design in the tendon, I think is 165 KSI. So I have to convert again there, apologies.
I mean, in terms of ultimate strength of the strength itself, do you stress to 75%? Is it okay to stress to 75%, or you do it lower?
Yeah, I mean, the code prescribes those numbers. I'm not sure I know exactly but it's around that 75. It's 270 KSI is the tendon strength, right? The ultimate strength.
270, okay.
Yeah. But as far as during the stressing operation, you do less than that, right? Because you don't want to get too close to the failure. So I think it's 70 to 80% when you stress it.
Okay.
But to answer your other question, more detailed about the systems, and you are right that when you take the conventional beam system out, you have to do more work with the core, with the shear walls, which sometimes means thicker walls, sometimes means more system. So sometimes when we take the beam system out, we may have to put in an outrigger system because otherwise the building wouldn't be stiff enough. So you're very much right that even though the flat slab has benefits, there are penalties in other areas such as thicker walls or maybe other components like outrigger system, depending on the building height and the needs. And on the weight and the thickness, I guess most of the economics comes if you can take advantage of the height reduction, right? Because you said, you're right in the material, that you can design a beam and slab system that has equal or less concrete in the floor system to a flat slab. I would say that a post-tension system is pretty efficient, and you have to be very accurate and precise with your beam system to save more concrete than a post-tension system. But you're right, it can be done. But the material savings mostly comes in reducing the height of the building. The less weight comes when you lower the building height. If you did the flat slab versus a beam and slab and you didn't change anything related to the floor-to-floor height, you don't have as much savings.
Something else to just add to that, because of the code minimum detailing provisions, when you put a beam in, you're obligated now, because I put a beam there, I must put in certain minimum reinforcing steel, no matter what. Stirrups, longitudinal bars, etc. And those minimums can add up and overtake the same minimums that you might see in a flat slab, because there's just fewer pieces and the limits are different. So the bottom line to all of it, right, is for each building, you have to assess. Is it better beam and slab and core wall, or is it better flat slab and core wall and outrigger? Again, it's not a very, what's the right term here? Off-the-shelf answer. Yeah. Each building has to be considered for its uniqueness.
Yeah.
I mean, each building has a different answer. So. You had a question a long time ago, so are you.
Any other questions?
Yeah, how about the maintenance if something is, if the building is already done and there is a earthquake and there is a crack? How about which one is easier and cheaper to repair?
That's a good question. I don't know that there's a lot of data that would argue strongly one way or the other. I'm not aware of any data that would scientifically answer your question. I think both buildings will experience cracking. Both buildings will require repair, and cracks will need to be injected. Which ones will be more versus less? Say this, that all of the buildings should be designed to the same drift limits. And the drift limits, if you're operating within those drift limits, that really is what is most relevant to how much damage will be in the building, irrespective of the system. And so you could say, well, in theory, they should have similar amounts of damage because they're both designed for the same drift limit. That's a very qualitative answer. I don't know that anybody has studied explicitly that, the answer to your question. It's very good in the sense that the future related to Sir Davies' question earlier about reliability analysis. Reliability analysis also informed by something called fragility curves. Maybe you've heard this term, fragility curve. And that is a way to explicitly answer your question. If you understand the fragility of the various parts and pieces of the building, and then can assess the demand levels against that fragility curve, now you can quantifiably answer the question. The problem is that we as an industry, as a design community, don't have enough of that kind of data yet developed. It's coming, but it takes time, right? No? Yeah. Yes, sir. In the back, yeah.
I want to know if we're using PBD and using the pre-stressing, how long the building can last as normal, or later on we need to retrofit again after how many years, or is there any time limitation for the pre-stress, like
The life of the pre-stressing?
yeah.
Yeah, I mean, not any less than rebar.
Yeah. There's no loss of pre-stressing force in
No,
terms of.
No, so there's the pre-stressing tendons that are specified are actually called low relaxation tendons, and they're specifically done to not elongate more over time. And once they're stressed, they're good. There is some losses that happen initially in the upfront, but not, 100 years from now it should be the same essentially. So there isn't a lower durability. I mean, there is some questions on unbonded post-tensioning and durability related to unbonded, in particular as it relates to making sure there's no water or anything that gets into the tendon, because then you can have corrosion issues. And corrosion is a problem, and it has an issue. And there have been buildings that have had those problems and have had to retrofit, or worse in some cases. But the bonded system actually helps prevent against that because you're fully encapsulating it with concrete. So, does that answer your question?
So in the code, there's no specification regarding the building
life.
Building life.
No.
No. And is it possible to use pre-stressing to reduce the vibration?
To reduce the what?
The vibration.
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 Floor vibration.
Like say we just the floor become driveway or parking sometimes.
Mhm.
Typically not.
Yeah.
Typically it's almost the opposite.
Yeah.
You reduce thickness.
Because your mass, the vibration control, mass is your friend. And by using post-tensioning, typically we're taking mass away.
Yeah.
So you have to be maybe more careful.
Hmm.
Most of the times, for most applications, we haven't seen vibration be that big of a problem. I'm certain there are certain applications where it's important. In the steel building, it's incredibly important. In the concrete building, because of just the mass of the structure, not so much, but occasionally, yeah, for sure. But the PT certainly doesn't make it better. It might make it work.
Yeah, I have a quick question here about post-tensioning in moment-resisting frames, or typically we call it lateral load resisting frames. We heard from design community that applying post-tensioning, especially bonded post-tensionings in the moment-resisting frame, will affect the ductility of the plastic hinge. So bonded post-tensionings is actually not allowed to pass through the plastic hinge region. So is this true, and how to go about it?
Yeah, so there was a very big research project that was conducted in the US in, I'm gonna say the early 2000s, maybe it was the late 90s. It was called PRESS, P-R-E-S-S. If you Google the PRESS research program, they studied a lot of these questions. There is today still remaining what's called a precast hybrid moment frame that was developed as a result of that research program. In the beam column joints region, it's reinforced with an unbonded tendon. But the beam itself could be from end to end of the beam could be bonded.
Yeah.
But precast hybrid moment frame, at least in U.S. practice, is kind of the one system that occasionally gets used. It's not very common, but it occasionally gets used. But yeah, I think that the concerns are real. But the research from the PRESS program, rather than we talk about this for the next day and a half, because we could. If you dig into the papers that were written associated with that body of research, there's a lot of really good information.
Yeah, but if we assign that frame system as part of the moment resistance frame system, and post-tensioning is there, especially bonded post-tensioning, and this would have to go through the plastic hinge regions.
Right.
So can we just simply, let the PT, the tendons to pass through it, or any special things?
So the technical concern is that there's no yield plateau on the PT tendons, and so as the rotational demands on the beam column joint go up, so goes up the stress in the tendon, and so goes up the shear demand on the joint. And so it's not that it can't be done, but it can't be done probably easily in a prescriptive environment. You need to definitely go to performance-based design and evaluate very explicitly what those rotation demands are and where you are on the stress strain curve of the PT tendon, because it will drive the joint shear. And that's really kind of the critical aspect of a moment frame design is the joint region. And you don't want to overstress the joint region. So if you can model it explicitly and thoughtfully consider it, then yeah, I'm sure you can do it.
Okay.
But it's probably not in a prescriptive environment.
But it means you have done it before, right? I mean,
No.
in one of your presentations, there is a white beam.
Shallow beam.
White beam.
Right.
And then that one will be the rotation of the plastic tube, right? Am I right to say so?
Yeah.
So you have done it before?
Yeah, so they're generally speaking, where the beam connects, say, to the core wall, that connection is done with mild steel, the PT stops short of the wall. And the testing that we did at Berkeley 20 years ago showed very clearly that's very important. That if you take the PT tendons, the anchorage, and put it at the wall, or even inside the wall, what it does is it concentrates the strain in the rebar and concentrates the cracking to a very small region, and the strain in the rebar goes through the roof and the rebar fractures. And so the way to prevent that is to take the anchorage zone and pull it away from the wall. Seems maybe counterintuitive, but you pull the anchorage away from the wall and you provide, I'll call it a gauge length, where just the mild steel is making the connection. And with the mild steel, then it can be ductile. And that was the research that we did at Berkeley, I don't know, 20 years ago. It was in the, maybe 15 years ago. And that was the outcome. We published a paper on this. We can send you the paper. And it's really critical to the performance of that. So, but it's not precast. That's a cast in place system.
Yeah, cast in place.
But if trend is stop or
Stop shop.
in between the wall and this one, that is also the what we call is maybe because the compression of this zone, this is a tension in this between.
Yeah, this is
Also
a really
create everything.
This is a shall we say commonly it's a common point of view. And let me give you an analogy to maybe help you understand why it's not correct. So if I have a slab with a core and making this connection, if I take the core away, so now I have a slab which is a donut, and I pre-stress my donut, the entire donut gets smaller. The connection's actually in compression because the entirety of the system got smaller. So the donut hole actually got smaller. It didn't pull away from the wall, it actually compressed. And this is something that I had exactly the same question when I was a young engineer, and I asked my boss, and he gave me exactly the same. We ultimately actually did some laboratory testing to prove that out. We weren't looking so much at a slab wall connection, we were looking at a slab column connection, where we had precast columns with a slab connection. I had exactly the same concern. Isn't the slab pulling away from the column? And by virtue of pulling away from the column, I have a shear friction interface problem. And the testing showed no, in fact, it's in compression because the overall of the system shrinks. So you can go do some computer modeling, you convince yourself. But that's the real outcome of it.
So the idea of using a PT flat slab in tall buildings is to fully rely on the core wall system for a lateral resisting system, right? And if it's really tall, you also combine it with outrigger system. Now you mentioned that your in your PBSD evaluation, you also model the micro outrigger effect from column to wall through the slab, and then you do elastic model with concentrated plastic hinges at the ends. Is that okay? So, which in a sense, kind of acknowledging that there's some stiffness contribution from that column slab wall connection, right? So, in your experience, how much of a contribution does this sort of micro outrigger effect contributes to in the global?
It's pretty small.
The numbers, again, it varies a little bit from building to building. 2% would be, if I saw a number that said 2%, I guess, I believe it. Just comparatively, because we've looked at this on a wide variety of buildings over 20 years. And yeah, some buildings it's 2%, some buildings it's 3%, some buildings are 1%. It's very small. When we proportion the system, typically we don't rely on this at all, right? The main thing we are looking at when we make that evaluation is what is the predicted increase on the column demand. If the column is just a gravity column, not intended to be part of the lateral load system, it's just there for gravity support, this micro outriggering phenomenon actually induces greater gravity, or adds seismic demand to what is otherwise a gravity column. And appreciating that increase in axial demand is something we look at carefully. Again, the number's fairly small, and usually it gets washed out in kind of load cases, if you will. That is, the gravity load case will take care of it. But it's a question that's commonly asked by peer reviewers of all our buildings, and we commonly respond to with the analysis and show that it's okay. But it should be looked at.
And as you said, it's excluded in the preliminary analysis. So like in our ETABS model, we make sure that that bending stiffness of the slab is not considered. So that's not that's not the intended load path,
Yep.
right?
Yep.
The intended load path is the core wall.
Yeah.
So we crack that bending stiffness of that slab very low so that it doesn't contribute significant to the strength of the system, just the strength of the system.
It becomes more important perhaps, or a greater contribution is if you have like an office building Sean was showing, where we use the wide shallow, the band beams, just because they're deeper, right? And so there can be a little bit more contribution. Once again, we proportion the system not considering their contribution to kind of the strength of the building. But then when we evaluate the building for its performance, we look at the rotational demands on the connectivity, and then the increased axial demand on the column.
So when you design that band beam, you detail it as a beam or as a banded slab?
Yeah, it depends upon the proportions. And we try to make it proportioned such that we don't have to follow all the minimums of the beam provisions.
Okay. Yep.
To make sure that, so you can have less rebar, it's more of a banded slab. So we call it wide shallow beam sometimes, but there's specific provisions in the code on the aspect ratio in order to make it more of a slab.
So it is a very optimized design.
Right.
I see. And that thing is part of your moment resisting system, or
No.
it's just gravity system?
It's just gravity system. The core in that project, the core is the entire system. I mean, if you think about it going from, let's just say, completely flat slab to a traditional conventional system, it's like in the middle as far as what it contributes. But even though it's in the middle, we still don't want to, we still say, we can do it all in the core system. Typically for office buildings, the core system tends to be a bit larger and tends to be not a problem to be able to do all of the work. And it's just cleaner and simpler to do it that way rather than try to rely a little bit here.
Yeah, it's a brilliant design.
Right, okay. So I think no more question. And thank you to Mr. Ron Klemencic and Mr. Son for the explanation. It's great explanation and valuable for us. And now to keep our performance, we have already prepared our lunch. So and a little break. Okay. Thank you so much. Thank you so much.
So I want to say, well, number one, thank you all for coming and spending time with us. And we hope that you learned some things and answered some of your questions. To the extent that you go away and have another question,